for determining the number of significant digits that are in a number. In this example, after the decimal place, if there are no preceding non-zero digits, then these zeros are not significant. So this number would only have 3 significant figures. In this example, because there is no decimal place after the zero is insignificant. Therefore, there are only 3 significant figures in this example as well. In example 3, this 0 is significant because it's between 2 digits that are non-zeros, and these 2 digits are also significant because of the decimal place that makes them significant. When you're multiplying numbers, the answer will have the same number of significant figures as the number that has the least amount of significant figures. So the answer to this one will only have 2 significant figures. When you're adding or subtracting, the answer will have the same number of decimal places as the number with the smallest number of decimal places, which in this case is 0.
Next I'm going to talk about the structure of the atom. The atom consists of a centrally located nucleus that is surrounded by an electron cloud. Neutrons have a neutral charge, protons are positively charged, and electrons have a negative charge. Although the proton and electron have opposite charges, they both have the same charge magnitude of 1.602 times 10 to the negative 19 coulombs. The proton has a mass of 1.672 times 10 to the negative 24 grams, and the electron has a mass of 9.11 times 10 to the negative 28 grams. And finally, the neutron has a mass of 1.674 times 10 to the negative 24 grams. The negatively charged electrons are attracted by the positively charged nucleus, and the approximate diameter of the atom is 1 angstrom, which in SI units is 1 times 10 to the negative 10 meters. The diameter of the nucleus is about 5 times 10 to the negative 15 meters, and surprisingly, the atom is mostly empty space, with the nucleus accounting for over 99% of the mass of the atom.
In chapter 3.4, we're calculating the masses of reactants and products. So for this problem, it says calculate the mass in grams of sodium sulfate that will be produced from the reaction of 200 grams of sodium hydroxide and sulfuric acid. So the first step is to write out the Dawn's chemical equation, which is there, and that's so you can get the mole ratio. And then you convert the given number of grams to number of moles of the reactant by dividing it by the molar mass of sodium hydroxide, which is 40 grams, and you get that there are 5 moles of sodium hydroxide. The next step is to convert that amount of moles to the moles of sodium sulfate by multiplying it by the mole ratio, which is 1 to 2, and you get that that's 2.5 moles of sodium sulfate. Then to find the number of grams, you multiply by the molar mass of sodium sulfate to get 355.1 grams.
In chapter 4, we see how to write aqueous ionic equations. First, we have to have our molecular formula, which includes all of the reactants and products. And to start writing our net ionic equation, we have to first write a total ionic equation, in which we divide each element, each ion, and we write all of them out. And in this one we have the cations and anions separate from each other. The next step to take would be to remove the spectator ions, which are the ions that remain the same on both sides of the equation, like nitrate and sodium. We see that they are the same, so we cross them out from our equation. That will leave us with just silver ion and the chromate ion, which would form sodium chromate. We can see that the net ionic equation is like the summary of the actual formula.
So in section 5.3, we studied the ideal gas law. Before we arrive at the ideal gas law, we have to talk about Boyle's law, which relates the volume of a gas is proportional to 1 over pressure. So they're inversely related. So as volume goes up, pressure goes down, and vice versa. For Charles' law, volume is directly proportional to temperature. And for Avogadro's law, the volume of a gas is directly proportional to the number of moles or the amount of gas. So when you combine these 3 laws, you arrive at what is known as the ideal gas law, which is PV is equal to nRT. So P stands for pressure, V volume, N amount of the gas, R is the universal gas constant, and T is temperature. What the ideal gas law allows us to do is to study the behavior of gases that are of the same type of atom, at room temperatures and pressures, moving randomly, and exerting no long-term forces on each other.
In chapter 6, we learn about Hess's law. Hess's law states that the overall enthalpy of a series of equations equals the sum of each individual equation. Enthalpy 1, 2, 3, and we can have many more. For example, if we know that the overall enthalpy of a series of reactions is 683 kilojoules, and that enthalpy number 2 equals 421 kilojoules, and enthalpy number 3 equals an exothermic 52 kilojoules, we can calculate the enthalpy number 1 by subtracting enthalpy 2 and 3 from the overall equation. That would be subtracting 683 kilojoules minus 421 kilojoules plus 52 kilojoules because the reaction is exothermic. And we'll see that enthalpy number 1 equals 314 kilojoules.
Next, in chapter 7, we've got the quantum mechanical structure of the atom. This is what we use today to normally describe what we look at, and use 4 different numbers to distinguish how it's orientated. First we have n, which is the orbital level of the electron. That can range from anything from n to 1, 2, 3, 4, or higher. Next we've got L, the shape of the orbital, which is usually limited by, can't be greater than n minus 1. That usually determines the different shapes of the orbitals. After that we've got M sub L, which is the orientations. Those are going to be restricted by the L, positive and negative versions of the L. And then after that is E sub S, which is the electron spin, which can be positive or negative, 1/2.
In chapter 8.3, we will be discussing periodic trends, which includes atomic size, ionization energy, electron affinity, and metallic character. Atomic size generally increases in this direction and is greatly influenced by the principal quantum number n and the effective nuclear charge. Next is ionization energy, which generally increases in this direction and is successive, which means that it has first, second, third, and so forth. There are some exceptions to ionization energy, and elements with low ionization energy tend to form cations, and those with high ionization energy tend to form anions. Next is electron affinity, which generally increases in this direction and is also successive, and also contains exceptions. Lastly is metallic character, which generally increases in this direction, and these are some of the characteristics of metals.
Okay, in chapter 9, we get an intro to metallic bonding. Some properties include mechanical, where electrons slide rather than pass each other. So we have the electron C, external force, and metal bends. Now the good conductors of electricity and heat because of the movement of electrons. Boiling point has a high boiling point because cations and valence electrons must break away from the others. Melting point, cations can move without breaking the attraction of surrounding electrons. So we go down a group, melting point decreases, we go across the period, it increases, and instead of forming compounds, they form alloys.
Next, in chapter 10.3, we've got the shapes of molecules and their polarities. The shape is based off the regions of high electron density, which we can describe as any bond being one region or any lone pairs being one region. Now when the total regions is equal to 2, we know that the shape of the molecule is going to be linear. When it's 3, we know it's going to be trigonal planar. When there's 4 regions, we know it's going to be tetrahedral, where there can be either polar, non-polar, different outcomes. When there's 5 regions, we know that there are multiple possibilities of either trigonal pyramidal, or we can have a seesaw, or even a T-shaped. When the region is equal to 6, we have multiple options of octahedral, square pyramidal, also T-shaped. These are all based off the different amounts of lone pairs in the molecule. For the polarity, we know that if the shape is not symmetrical, it's going to be polar. But if the shape is symmetrical, we know it's non-polar.
In chapter 11.1, we will be discussing valence bond theory and orbital hybridization. And the valence bond theory explains that a covalent bond is formed when the orbitals of 2 atoms are overlapped and the electron pairs occupy the overlapping region. And to further that idea, the valence bond theory explains molecular shape as presented here in this chart. And in order to find hybrid orbitals, these are the steps.
Step 1, molecular formula. Step 2, Lewis structure. Step 3, electron group arrangement. And step 4, hybrid orbitals.
Over here, we have an example of sulfur tetrafluoride. Step 1, you have the molecular formula. Step 2, draw the Lewis structure. Step 3, you have the electron group arrangement. And then step 4, you have the orbital, which is trigonal bipyramidal with the orbital sp3d. And an easier way to do this would be to circle the lone pairs and bonds. So 1, 2, 3, 4, 5, s, p, 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 d, and you have sp3d.